You probably know the board game Mastermind, right? The colored pegs, the hidden code. But what if I told you that cracking this simple game actually holds a key to a major breakthrough in artificial intelligence? Well, today we're going to dive into how a totally new way of thinking about information created a near perfect AI mastermind player and what that could mean for the future of strategic thinking itself. So let's start with a big question. What's actually the smartest way to play Mastermind? I mean, it sounds simple, doesn't it? Is it just about getting lucky, making a random guess, and hoping for the best? Or is there some perfect mathematical strategy that guarantees you'll find the answer in the fastest way possible? For decades, computer scientists have been wrestling with this exact problem. And the journey to the answer, well, it tells us something really profound about what information really is. All right, first up, let's talk about the Mastermind Challenge itself. And believe me, this is way more than just a kid's game. For a computer, this is a serious logic problem. It's about navigating this huge, sprawling space of possibilities to find one single correct answer. Okay, so for anyone who hasn't played in a while, here's a quick rundown. In the standard game, you've got 4 slots and 6 possible colors. Someone, the code maker, sets a secret code. Your job as the codebreaker is to guess it. And after every single guess, you get feedback. You get bulls for a correct color in the right spot and cows for a correct color but in the wrong spot. The goal? Crack that code in as few turns as you possibly can. And here's where it gets kind of nuts. This is the scale of the challenge. With 6 colors and 4 positions, and yeah, you can repeat colors, the number of possible codes is 6 to the power of 4. That's 1,296 potential secret codes. Every single guess you make has to be an intelligent attempt to just slice down that massive list until only one possibility is left. So, how in the world do you teach a computer to play this? Well, the first attempts were all about the math, a purely numbers-only strategy that was built on this really powerful idea from information theory. And that idea is something called Shannon entropy. Think about it like this. If you were looking for a name in an old school phone book, you wouldn't start at the A's, right? No way. You'd open it right to the middle. In one move, you've just eliminated half the book. Shannon entropy tries to do the exact same thing for Mastermind. It picks the one guess that, on average, will split that pool of 1,296 codes into the smallest possible chunks, just maximizing the raw amount of information you get back. But, and this is a huge but, this whole approach has a major flaw. Shannon entropy is completely blind to the strategic nature of the game. It basically thinks all information is created equal. It only cares about making the list of possible answers smaller, not about whether the options that are left are actually easy or hard to solve. And this right here is the absolute key to the whole thing. It's about 2 different ways of thinking about information. You have quantity versus quality. The old method, Shannon entropy, just asks, how much did my guess reduce the number of possibilities? But the new method, weighted entropy, asks a much smarter question. How strategically useful is the clue I'm about to get? That tiny shift in perspective, it changes absolutely everything. Which leads us to the core idea of this whole breakthrough, the quality of a clue. It's this simple but incredibly powerful realization that, you know what, not all feedback is created equal. So here's the problem in a nutshell. The old strategies just assumed that every single clue, every combination of bulls and cows you could get back, was just as valuable as any other. And the breakthrough, it's something that feels so, well, human. I mean, if you've ever played the game seriously, you know this feeling. You know that some feedback gives you a really clear path forward, while other feedback just leaves you totally stuck, scratching your head between a dozen confusingly similar options. This new AI was designed to finally capture that intuition. So, how do they do it? The mechanism is called weighted entropy, and it is seriously brilliant. It's an extension of that old idea, but instead of treating all 14 possible types of feedback as equal, it gives each one its own unique utility score, a weight. So the AI isn't just hunting for the guess that gives it the most raw information anymore, it's hunting for the guess that's most likely to give it the most valuable information. So, for instance, the AI eventually figures out that getting a clue like 1 bull, 0 cows back is way, way more helpful than getting 0 bulls, 4 cows. And it's not about the numbers themselves. It's because that first clue creates a much simpler, cleaner problem to solve on your next turn. It's about thinking about the strategic landscape, not just the raw data. Okay, so this is all great, but it begs a massive question, right? How on earth do you figure out the perfect utility weight for every single one of those 14 feedback types? Well, the answer is you get the computers to teach themselves, using a process that's basically modeled on evolution. They use something called a genetic algorithm, and it's basically survival of the fittest for AIs. Here's the rundown. First, you create a whole population of AI players, each one with a totally random set of weights, a random strategy. Step 2, you make them all compete. They have to play every single one of the 1,296 possible games. Step 3, the winners, the AIs that did the best, get to breed, and they combine their strategies to create a new, hopefully smarter generation. And step 4, you do that again, and again, and again. 50,000 times until you've evolved an absolute monster of a player.
All right, so after 50,000 generations of this digital evolution, what happened? How good did this AI, the one that values the quality of a clue, actually get? The results are, well, they're stunning. Honestly, the results really speak for themselves. Famous strategies like the one from computer science legend Donald Knuth, his is a minimax strategy, which means it always plays to avoid the worst possible outcome. It averages about 4.47 guesses. The classic Shannon entropy we talked about, a little better. But this new weighted entropy approach, it gets the average down to just 4.348 guesses. That's a huge leap forward, and it gets breathtakingly close to what we think is the theoretical perfect score. Let's just break down how impressive this is. The AI comes within just 0.2% of a perfect score. It blows past the other best strategies. And maybe the coolest part? The AI discovered something that took human players ages to work out. It learned that the best opening guess isn't the one everyone starts with 1, 2, 3, 4. It's 1, 1, 2, 3, a guess with a repeated color, because it actually probes the problem in a much more efficient way. So, what's the big takeaway here? What does this all mean? Look, this isn't really about a board game. It's a proof of principle. It shows us that by teaching an AI to understand that some information is just strategically better than other information, to value quality over sheer quantity, we can unlock near-optimal performance in really complex problems. And that really leaves us with a huge, exciting question. If this approach can get us this close to perfection in a game like Mastermind, where else could we use it? Imagine a doctor trying to pinpoint a rare disease from a list of symptoms, or a scientist searching for a new material. In any field where we're basically looking for a needle in a haystack, what could we achieve by building AIs that don't just gather all the data they can, but instinctively know which clues are the ones that truly matter?